Hello, I'm Mr. Rose, and today we're going to be discussing the work-energy theorem. Today's problem is coming out of the text, Young and Freeman. It is Chapter 6, Question 19. Please see the text for the full description. Brief descriptions appear in each section. So to start, we're starting with Part A, a branch falling from a tree. What we're going to do is we're going to use the work-energy theorem, which simply states work is a change in kinetic energy. We're then going to check each problem with our kinematics equations. So our very first one, like I said, we have a branch falling from a tree. We're stating that work is equal to force times distance, or F dot D, and then our change in kinetic energy. Kinetic energy is 1/2 mv squared. So our change in kinetic energy is our final velocity minus our initial velocity. Since our tree branch is falling from rest, we know the initial velocity is 0. And since it's falling, I know that force is just the force due to gravity. Here I have m times g. And I'm calling it positive because everything is going with the positive direction. The force and gravity are both going down. I cancel out my masses. I'm left with just gravity times distance is 1/2 times v final squared. Simple algebra gets a final velocity hitting the ground of the square root of 2g times d. Now checking with my kinematic equations. Here I have v squared equals v naught squared plus 2ad, or a times delta x. We know our initial velocity again was 0. Simple check, or simple algebra rather, we know v is equal to the square root of 2a times d, where a is just that acceleration of gravity. We see those two things are the same. For part B, we're doing the exact opposite. We now have a volcano shooting something way up into the air. So again, I'm using my work kinetic energy theorem. Work is F dot D is equal to our change in kinetic energy, which is just 1/2 m final squared minus 1/2 m v initial squared. This time, my force due to gravity, we're shooting up. So the force due to gravity goes down. My object is going up in the air, so I have that negative sign there going against gravity. Negative mgd, there's my force due to gravity, equals 1/2 mv final squared minus 1/2 v initial squared. This time at my maximum height, something we know, is the velocity goes to 0, so that whole section cancels out. Again, I cancel out my masses. I'm left with a negative g times d is equal to negative 1/2 mv squared. My negatives cancel out. Again, I'm left with a v equal to the square root of 2 times g times d. Again, those two things should be equal, except for my mistake in notation. Going to part C. Part C, we're going to use the work energy theorem to find out what happens to a skier that's just traveling at a constant velocity that all of a sudden hits a patch of friction. So we're starting with work equals our change in kinetic energy. Again, work is F dot D is equal to 1/2 mv squared minus 1/2 mv initial squared. Now, in this case, my frictional force is my force is a frictional force, which I'm noting as a negative Fk. It's kinetic friction because, again, he's moving. And that negative sign is because friction is moving or is acting opposite motion. So I know friction is mu k times the normal. My normal is m times g. My distance is my distance. And since it's asking me when the skier stops, I know my final velocity is 0, so that whole thing cancels out to 0. So I'm really left with a negative mu k times g times d is 1/2 v naught squared. Rearrange my equation. I know the skier is going to travel some distance equal to 1/2 his initial velocity squared, divided by the coefficient of friction between the skier and the snow, mu times g. To check again with kinematics, v squared is v naught squared plus 2ad. Here I'm saying acceleration using Newton's second law is F over m. Just rearrange my equation, subbing in for acceleration, but noting that my force is my frictional force, negative mu times m times g. Again, that negative mu because my frictional force is going the opposite direction of motion. I know my final velocity is 0 as stipulated by the problem. Bring my initial velocity over, negative v naught squared equals 2 times my frictional force, negative mu mg, divided by my mass from my definition of acceleration times the distance. I cancel out my masses. Rearrange my equation, and again, I have distance as 1/2 times the initial velocity squared over my coefficient of friction divided by gravity. Again, we can see both things check out. Moving forward, how fast would that, instead of just the distance, now I want to know how fast would the skier be going if that patch of friction was just small, not large enough to stop it. We're going to go through the exact same format again. Work is our change in kinetic energy. Again, my work is F dot D, where the force is my frictional force. So I have my frictional force times some distance is equal to my change in kinetic energy. Again, I know my frictional force is negative mu m times g. Multiply that by the distance. This time, my velocities don't cancel out because I'm looking for my velocity. I had an initial velocity. I'm looking for a final velocity. I cancel out all my masses. Negative mu times g times d is I pulled out my 1/2 v squared minus v naught squared. Again, simple algebra, multiplying both sides by 2, adding my initial velocity to both sides. I find that the skier's final velocity is equal to the square root of 2 times the coefficient of friction, g times d, plus his initial velocity. Checking that again with kinematics, v squared equals v naught squared plus 2ad. Again, we're using the same equation here over and over again. I know my acceleration is force divided by mass, and again, I know that force happens to be my frictional force. That frictional force, negative mu times m times g. I'm going to cancel out my masses as you see here. Rearrange my equation again. We have, again, the exact same equation. Velocity is v squared minus 2 mu gd. Only difference is the order of my variables. Again, in adding and subtracting, this is totally okay. Last is the most difficult conceptual question, is how far up a hill would a skier go if there was, again, no friction, but he's just being slowed by the acceleration of gravity. Because we're using the work-energy theorem, we're completely path independent, which means it doesn't actually, I don't need to break anything up into components here. So that being said, I know F dot D is 1/2 mv squared minus 1/2 mv naught squared. My work is equal to my change in kinetic energy. My work is just the work against gravity since I'm going up. Again, I'm noting that as a negative. Negative mgd is 1/2 mv naught squared, where my final velocity was 0, so I lose that entire term. We get a distance, this is a vertical height off the ground, is equal to 1/2 v squared over g. Again, that is just the vertical height. If I wanted to find out how far he was parallel to the plane on that slope, I would need to account for the angle. Checking it with kinematics, again, this would just be my y height or my y distance. V squared equals v naught squared plus 2ad. Simple math here. My final velocity is 0. Bring over my initial velocity. We find out my distance, negative v naught squared over 2a. Exactly the same thing, 1/2 v naught squared over g. This is very, very powerful work kinetic energy theorem. We can shortcut a lot of kinematics and start to do things a little bit more efficiently. That's it for our work energy theorem. I want to leave you with a quote as Terry Patrick, I believe, once said, "In the beginning, there was nothing, and then it exploded." Please comment, like, subscribe, and I'll see you next time.